Section 21.9, Isomerization reactions. The isomerization of a transition metal complex may involve ligand substitution, bond cleavage and reformation, or twisting. In previous sections, we talked about ligand substitution. So in this section, we will focus on the last two different types of isomerization: bond cleavage and reformation, and twisting. First, bond cleavage and reformation. It can change the structure of the transition metal complex. So now let's look at this transition metal complex. This cobalt is bonded to this bidentate ligand. This cobalt is bonded to this bidentate ligand. We don't care about the detail of these two ligands. This cobalt is bonded to a third ligand. This ligand is actually a tridentate ligand with 3 oxygen atoms. Potentially can all donate electrons to the transition metal center. However, if you just examine this structure, this is actually a planar structure over here. The main structure is planar. So these two are close enough to this cobalt and can each form a sigma donor bond here and here. The third tooth is just too far away. You may imagine this is a vampire, okay, with 2 teeth biting into this cobalt. The third tooth is on the back of the head of the vampire, okay, so that it's impossible for this vampire to use this tooth on the back of his head to bite into the same person. All right, so only 2 bonds here. And also I want to talk about this, the charge of this ligand. It bears a negative charge. And you can say this negative charge is here, or negative 1/2 on here and negative 1/2 on here. Why? Because you can draw 2 Lewis structures. You can say this oxygen is neutral. It forms a double bond with this carbon. Okay, neutral oxygen with 2 lone pairs. And this is a double bond. And then this is a single bond, double bond, single bond. And this oxygen is negatively charged with 3 lone pairs. And this O- with 3 lone pairs uses only 1 lone pair to form a sigma donor bond with this cobalt. Okay, this oxygen is neutral with 2 lone pairs. It can also use 1 lone pair to form a bond. All right, but also you can draw the other Lewis structure with the negative charge on this oxygen. Okay, so this oxygen is O-. This O- has 3 lone pairs, and this is a single bond, and then this becomes a double bond, single bond, double bond, and this oxygen is neutral. So 2 resonance structures. But on average, you can say, well, we have negative 0.5 charge on here, negative 0.5 charge on here. This bond order is 1.5, 1.5, 1.5, 1.5. All right, so that's why you draw a curve here. It indicates we have just partial pi bonds here. And that's why this is actually a planar structure. So this is a planar structure. This bond, this bond, this bond, this bond, this bond, this bond, this bond are all on the same plane. All right, on the same plane. Okay, now let's break a bond. We can break any one of these 2, but in this picture, I think this bond is broken. How can we break a bond? Well, it's just maybe thermal energy. This complex collides with some other surrounding molecules and accumulate enough energy to overcome the barrier to break this bond. I know it's hard to break this bond because there's also a chelate effect, etc., etc. But anyway, the bond is broken here due to the collisions, maybe. And then we go from here to here. This is really easy, going from here to here. I think you just need to kind of, look at this same structure from a different angle. You kind of need to kind of move this to here, move this 2 bidentate ligands to the left-hand side, move this ligand to the right-hand side, and you need to rotate some single bonds. Okay, I'll let you do that. I'll let you rotate some single bonds. And when you do that, you can somehow have This oxygen, okay, this oxygen is different from this one because you can see this oxygen is double bonded to this carbon, and this carbon is bonded to CD3. This carbon is bonded to CH3, so these two oxygens are different. All right, so now you can go from here to here really easily, and then this oxygen is really close to the cobalt. Okay, in here this oxygen is close to cobalt. In here this oxygen is close to cobalt. You just need to do some rotation of some single bonds. All right, so this is achievable. Okay, now it's possible for this oxygen as a sigma electron donor to form a bond with this cobalt transition metal center. So the bond is formed. So this is called a bond cleavage here, and a bond reformation here. All right, bond cleavage and reformation. And now you have a different structure over here. These two oxygens are close to these two methyl groups, but over here, if you examine these two oxygens, one of these two oxygens is bonded to this carbon, which is bonded to CD3 instead of CH3. So now you look at the third tooth here on the back of the vampire. It's actually close to a methyl group. All right. Now let's look at twisting. First, I want you to picture a trigonal prism structure in your head, made of wires. Just wires, okay, flexible wires. All right, 1, 2, 3, 1, 2, 3, 1, 2, 3, 9 wires. Okay. And now I want you to rotate the top triangle just 60 degrees. All right, this is trigonal prism. Just rotate this 60 degrees. All right, so right now you're looking at this triangle and this triangle are in the eclipsed conformation. So after you rotate this only just 60 degrees, this vertex will be here, this vertex will be here, and this vertex will be here. All right, and this is now a staggered conformation. Okay, picture that in your head. All right, so right now these two kind of are aligned, these two are aligned, these two are aligned perfectly. It's eclipsed. But once you rotate the top triangle just 60 degrees, counterclockwise, this vertex will be here. Okay, it's going to be on the opposite side to this one. If you can imagine a staggered conformation of ethane, C2H6, you know what I'm talking about. And this will go here, and this will go here. So all three colored linkages, okay, will appear in a non-parallel position. All right, non-parallel position, because this one will go here. So somehow you need to imagine this red will be kind of like this way, okay, like this way. It's not going to be vertical. Right now it's vertical, but you're going to rotate this guy to here, so it's going to be like a little twisted, okay, a little twisted. And this one will go here, a little twisted, so it's going to be like this. Okay, the blue will like this, the blue will like this, the red will be like that, and finally the green. Okay, this vertex will be here, somewhere here. Okay, it's going to be also a little twisted. And also, if you rotate this triangle 60 degrees, it's going to be octahedral. It's going to be octahedral. So if you rotate this 60 degrees, you may call this anti-trigonal prism. But then if you just examine this vertex will go here. If you examine this vertex and this vertex, these two will become the top and bottom of an octahedron. All right, so if you have a hard time picturing this, I think you can just look at this triangle. Okay, this is a equilateral triangle here. Okay, it doesn't look like one because of the orientation of this octahedron, but this is a equatorial triangle. Okay, and then I want you to look at this equatorial triangle. Look at this vertex and this vertex. They are in the staggered positions. These two are in the staggered positions. These two are in the staggered positions. So if you look at this triangle and this triangle, okay, you can see these two as in the staggered positions, and you can view this structure as anti-trigonal prism structure. All right, so that's why you can go from here to here just by twisting, and you can go from here to here by twisting. Same here between these two, the top pass is called a Baylor twist. The bottom part is Reed twist. But anyway, there are different ways of twisting the octahedron to trigonal prism and back to octahedron. There's another way to rotate or to twist this octahedron to a different trigonal prism and then to another octahedron. So two different pathways. And either way, if you look at the initial configuration here and the final configuration, you can see these two are different. You can look at those three links with different colors. You will get a different configuration. There are two different mechanisms. Again, the top one is called Baylor. The second one is Reed.